Hello everyone and welcome to our second video of Unit 3. Today we are talking about conditional and biconditional statements. Conditional statements are logical statements that have two parts, a hypothesis and a conclusion, written in an if-then format. So if we're looking at our symbols, we're just going to write down our if-then format to start. So I have if something, then something else. We show our if-then statement using an arrow. So it points from left to right. If something, then something else. In a conditional statement, it says we have two parts. We have a hypothesis and a conclusion. The hypothesis is the part P of a conditional statement following the word if. So the hypothesis comes right here, and we're going to represent that using the letter P. So if P, then something else. So then in our symbols, we would say P. So this reads if P, then, and we don't know what comes next yet. Because I'm using P for the hypothesis and I'm writing the P in green, I'm going to go ahead and highlight the word hypothesis in green over here. So hypothesis is green, goes with the P. For our conclusion, we're going to do the same thing. I'm going to use the color blue for conclusion, and our conclusion is the part Q of a conditional statement following the word then. So in other words, we have if hypothesis, then conclusion. And we represent that conclusion using a Q. So I have a lowercase q there. If P, then Q. If P, then Q. If the hypothesis, then the conclusion. All right, let's take a look at an example. So we have example 1, write the statement as a conditional. X is odd and 2x is even. All right, so we have if something, then something else. That is our format of a conditional statement. So I'm going to start with my purple from before. So the if-then part will be purple. If, oh, my color didn't change. Let's try that again. If something, if my hypothesis comes first. So if x is odd, so x will be my hypothesis. So if x is odd, then we have our conclusion. So if x is odd, then, using blue to represent my conclusion, 2x is even. So if x is odd, then 2x is even. And that is my conditional statement. So I'm taking something and I'm splitting it into two pieces, the hypothesis and the conclusion. If, then. If the hypothesis, then the conclusion. If x is odd, then 2x is even. All right, so now we have something called a truth value. A truth value does two things. One, to show that a conditional is true, show that every time the hypothesis is true, the conclusion is also true. And to show that a conditional is false, find only one counterexample for which the hypothesis is true and the conclusion is false. So what we're really getting at here with the truth value is we're trying to say that a conditional statement is either true or false. So let's go ahead and write that above. So a conditional statement and remember a conditional statement is an if-then statement, is either true or false. That's essentially what these two things are saying here. So let's look at an example. Example 2 says, is the conditional true or false? If it is false, find a counterexample. If a polygon has 6 sides, then it is a hexagon. All right, so let's think about that. A polygon has 6 sides, and a hexagon means 6 sides. So right now this is sounding like it's true. So a regular hexagon looks something like this, where all sides are the same and all angles are the same. That's what we call a regular hexagon. What if we had a six-sided shape like this, where I have 1, 2, 3, 4, 5, 6 sides. The sides are clearly not the same length. The angles are not the same. Is it still a hexagon? And the answer is yes, because it just has to be a figure made up of 6 straight sides, which we have. So this is a true conditional. So we would say the conditional is true. Now let's say this said that it was a regular hexagon. If it said a regular hexagon, then we would say false. You would draw this shape or something else like it and say false because this is a 6-sided polygon that is not a regular hexagon. That would be when it would be false, and that's how you would show a counterexample. All right. We have a few more definitions to go through here. So we have conditional statements. Conditional statements are statements that say, if hypothesis, then conclusion. Or in other words, we would say, if P, then Q. We already kind of talked about that one. So we would write that as P, arrow, Q. If P, then Q. The converse of a conditional statement exchanges the hypotheses and the conclusion. So before we said, if hypotheses, then conclusion. Now we're flipping them. So now we're saying, if conclusion, then hypotheses. Or in other words, if Q, then P. So if Q, then P. And we would write that as Q, arrow, P. If Q, then P. All right, next we have the inverse statement. The inverse statement is something that negates both the hypothesis and the conclusion. So we come back up to the conditional statement, and instead of saying if P, we're going to say if not P, then not Q. So we have if not P, then not Q. So we draw a negated P and Q using something called a tilde. So I have if not P, then not Q. Not P, not Q. If not P, then not Q. All right. Last but not least, we have the contrapositive. The contrapositive takes the converse and flips to negating them. So I now have if not conclusion, then not hypotheses. Or if not Q, then not P. So I'm going to say in my symbols, the tilde, so not Q, arrow, not P. If not Q, then not P. That's how this reads right here. All right, now that we've taken a look at the statements in their symbols in their basic form, we're going to go ahead and look at an example that uses some words. So I'm going to flip the page here, and I have up here this example 3 that says, write the conditional, converse, inverse, and contrapositive statements for each and tell if they are true or false. So I have the conditional, P then Q, converse, if Q then P, inverse, if not P, then not Q, contrapositive, if not Q, then not P. All right, so starting with the conditional, and I have this statement, pianists are musicians. So I'm going to split that into 2 pieces. So if you are a pianist, then you are a musician. All right, Next we have the converse, where we flip that. So if you are a musician, then you are a pianist. If you are a musician, then you are a pianist. If it helps you, instead of just recognizing the piece and flipping them, if it helps you, I would write out at the top. So P would represent the pianist, and Q is representing musician. You can write that a little more full. You can write the separate pieces. This is enough for me, so I'm going to leave it like that and just fix it in the sentence. Alright, so now I have my inverse, which takes the conditional and negates it. So if you are not a pianist, then you are not a musician. If you are not a pianist, then you are not a musician. All right. Next we have our contrapositive, which says if not Q, then not P. So we're going to take our converse and we're going to negate it. So if you are not a musician, then you are not a pianist. If you are not a musician, then you are not a pianist. Alright, so now that we've written our statements, we want to take a look at their truth values. Is it a true statement or is it false? So the conditional, if you are a pianist, then you are a musician. Is that true? Yeah, it is. If you play the piano, you are a musician. So that's true. Then it says, if you are a musician, then you are a pianist. Do all musicians play the piano? No. So this is a false statement. Next, if you are not a pianist, then you are not a musician. So if you're not a pianist, then you're not a musician. So that's saying, once again, that you can only be a musician if you play the piano. And that's not true, because you can be a musician and play another instrument. So that would also be false. And the contrapositive, if you are not a musician, then you are not a pianist. If you're not a musician, that's saying that you can't play any instrument at all, or sing, or any of those things. So if you can't do any of that, then you can't be a pianist, because we already said that pianists are musicians. So this is a true statement, because if you are not a musician, then you can't be a pianist. All right, look at something interesting here. The conditional and the contrapositive were both true, and the converse and the inverse were both false. Well, there's a reason that happened. The conditional statement and the contrapositive statement work together. If one of them is true, the other should also be true. So the conditional is true, then the contrapositive will also be true. The converse and inverse work together too. So if the converse is false, then the inverse will also be false. If the inverse is true, then the converse will also be true, and vice versa. So, when you're solving a problem like this, if you get false for the converse, you already know that you can say the inverse is false. Same with the conditional. If you get the conditional is true, you already know the contrapositive is true. If you still want to read through and think through it and find the answer, it will work. You're going to get there. But you don't have to think through it as much, because we already know if the conditional is true, so will be the contrapositive. Alright, so those were all conditional statements. Now we're going to take a look at biconditional statements, which takes some of these pieces and mixes them together. So a biconditional statement is a statement that is written in the form P if and only if Q. This means if P, then Q, and if Q, then P at the same time. both of these statements are inside this one statement. So it reads from left to right. If P, then Q, and if Q, then P. P, if and only if Q. There is one shortcut here that we want to use, and that is right where it says if and only if. We write that. It kind of looks a little funny how we write it, but we write that as IFF. If and only if. That's what that means. This is an official abbreviation. You're going to see this elsewhere. I'm going to use this from now on. You can write this on your test and your homework and your practice questions as well. P, if and only if, Q. All right, let's look at an example. Example 4. Using the statements P and Q below, write the symbolic statements in words. A, we have P, you passed the test. Q, you scored 60% or higher on the test. And we're saying, with this symbol, should also probably write that up here, that the biconditional statement, if and only if, is represented by a double-sided arrow. So P, if and only if Q. So I can say, you passed the test. If and only if, all I have to do is write IFF, if and only if you scored 60% or higher on the test. All right, so there's one example. Let's do another one. Part B. P, if and only if Q, where P is 3 points are collinear and Q says the points are on a line. So I can say 3 points are collinear. 3 points are collinear if and only if the points are on a line. All right. We have one more example here, example 5, that says to rewrite the biconditional as a conditional and its converse. So when we were saying up above that the biconditional statement is both if P then Q and if Q then P, that means that we can take a pre-made biconditional statement and split it into two separate statements, the conditional and its converse. So if I have the car will run if and only if there is gas in the tank, it's already put a natural split inside of our statement here. So we have the hypothesis on this side and we have the conclusion on that side for our conditional statement. So I have for my conditional, well actually let's take a second here and break this down. So we have my P and my Q on the other side. So if the car will run, then there is gas in the tank. All right, that's my conditional. Now I need my converse. My converse takes that and flips it. So I have if Q, then P. So if there is gas in the tank, if there is gas in the tank, then the car will run. All right, so we have a conditional and a converse. The car will run, then if the car will run, then there is gas in the tank. The converse, if there is gas in the tank, then the car will run. All right, so this is our last example on this page. We're going to go ahead and flip the page because biconditionals have truth statements as well. So a biconditional statement can be true or false. To be true, both the conditional statement and its converse must be true. So let's look at an example. Write the converse of the true statement. If the converse is also true, combine the statements into one biconditional statement. So I have this conditional that says if an angle measures 90 degrees, then it is a right angle. And I already know it's true because it said it was true in the instructions, but that's a true statement. We know that. So the converse then, we would take that and say after then, we'd put that in front after if. So if it is a right angle, then the angle measures 90 degrees. Is that true? Yes, it is. Right angles measure 90 degrees. Because both of these things are true, now I can put them in a biconditional, and that should also be true. So I'm going to circle that right now because I already know if these two things are true, this is true as well. So my biconditional is a right angle an angle measures 90 degrees if and only if it is a right angle. Oop, I'm mixing my words together. Let's fix that. If and only if it is a right angle. And we do know that's true. All right, let's look at another one. The conditional, if point C is on ray BA, then point C is on line BA. All right, we're saying that's a true statement. Now let's look at the converse. If point C is on line BA, then point C is on ray BA. All right, so if it's on the ray, then it must be on the line. If the point is on the line, does it have to be on the ray? No, because the line continues past B, but the ray starts at B and only goes towards A. So if on our line, point C is before B, then it's not on this ray, so that's false. So I can still write my biconditional statement, but my biconditional statement is now going to be false because these aren't both true. So my biconditional would be C is on ray BA if and only if C is on line BA. By the way, from our first unit, we know that saying point and then C is a little redundant, so I can say C is on ray BA and know that that's a point, and I don't actually have to write ray in front of BA because this arrow above it tells me that already. All right, so we've seen a true example and a false example. Now we want to look at what happens when we have definitions as biconditionals. In geometry, biconditional statements can be used to write definitions. A definition, let's try that again, a definition is a statement that describes a mathematical object and can be written as a true true biconditional statement. Most definitions in a math textbook aren't written as biconditional, but they can be. The if and only if is implied. For example, number 7, we have a triangle is a 3-sided polygon. If I write that as a biconditional, it will be true and it will be a definition for a triangle. So I can say it is a triangle, or a figure is a triangle. A figure is a triangle if and only if it is a 3-sided polygon. That's a definition for a triangle written as a biconditional. A figure is a triangle if and only if it is a 3-sided polygon. That means I can flip it and it will still be true. So if a figure is a 3-sided polygon, then it is a triangle. All right, in example 8 here, we have which is a good definition, has no counterexamples, and could be written as a biconditional. So we're going to start with the biconditional piece. A fish is an animal that swims. So if a fish is an animal, then it swims. Okay? If an animal swims, then it is a fish. Okay, that's false because all or other animals can swim. For example, a hippo can swim, and it is not a fish. Hippos swim, so do dogs. We could go with a dog if we wanted to, and aren't fish. Rectangles have 4 corners. If it is a rectangle, then it has 4 corners. If a shape has 4 corners, then it is a rectangle. Okay? So, if we think about that, the definition of a rectangle is that it is a 4-sided shape where the 2 opposite sides are congruent and all corners are 90 degrees. Well, parallelograms don't have to have 90 degrees. So we're going to say false and say parallelograms don't have to have 90-degree angles. All right, giraffes are animals with very long necks. If it is a giraffe, then it is an animal with really long necks. If the animal has a very long neck, then it is a giraffe. Okay, that doesn't work because ostriches have very long necks and they're not giraffes. So we can say false, and our example is an ostrich. I don't really know how to spell that, so that's my guess. False, ostriches also have long necks. A penny is a coin worth 1 cent. If it is a penny, then it is a coin worth 1 cent. If it is a coin, then it is if it is a coin worth 1 cent, then it is a penny. If we're sticking with US money, which we're going to, then this is true. So this is our answer. That is our true statement. A penny is a coin if and only if it is worth 1 cent. All right, this is where we're going to stop for today. There was a lot of information in this lesson as we were covering both conditionals and biconditionals, and I think the difference can sometimes be a little confusing. So we'll do the best we can to get a lot of practice in during class so that we can have a good understanding of conditionals and biconditionals. We will pick back up in our next lesson where we will prove some theorems that we already know.